Today we're going to talk about electrochemistry, specifically redox reactions and oxidation states. So to begin with, what we see here is a picture of a typical electrochemical reaction that encompasses both lighting up a light bulb and a salt bridge, but basically it's the whole idea that we're having electrons to pass through a wire, so that's called current, so the flow of electrons is current, and so that flow of electrons is passing through the wire, and it's entering in the light bulb, making it glow, continuing back on to complete the circuit. And basically, the thing that's causing that flow of electrons is the fact that you have two different metals. So the idea you have dissimilar metals. So you have iron on the left side, and that's where oxidation is occurring, copper on the right side, and that's where reduction is occurring. So where this whole idea for a salt bridge and for electrical current to be flowing, one of the original ideas that brought this all about was when you got Alexander Volta a long time ago. What was happening was they were performing surgery, and what he did was he was holding onto some piece of metal, and theory says, or history says, that his nurse was touching the patient, which was a frog at that moment, with a different type of metal. And what they noticed is somehow they grounded each other and they caused a jump that caused the frog to jump. And so what happened is they were actually passing current through the frog because they had two different metal scalpels that were working on the frog simultaneously. So that's kind of the idea too behind our defibrillator, when you go, okay, clear, and you put it on somebody and you help, rejuvenate the heart by passing electrons through the body and causing electrical shock and just getting the heart to pump like it's supposed to. But that's a long way of saying that this is a salt bridge, and that's where the whole idea came from. But mainly it relies on one thing: dissimilar metals. If you don't have two different metals in this reaction, you won't have what's called a potential difference, and you won't have stuff flowing. So in today's lecture, what we're doing is we're looking at the differences in the metals, or the differences in oxidation and reduction, to help us understand what's happening that causes this electron flow. So a redox reaction is called a redox reaction because you have read, which is reduction, and then ox, which is oxidation. And the idea is you will never have oxidation occurring all by itself. Whenever oxidation occurs, you are producing electrons. You're losing the electrons. Whenever something's being reduced, you're gaining electrons. You can't just lose electrons into thin air. They have to go somewhere. So redox reactions means that you will always have to have one with the other. And so oxidation, reduction. If you're losing electrons, something else is going to gain them. And so you always have them in a pair. So that's why they're called redox reactions. These at the bottom are a couple of different kind of catchphrases that students have used to help remember which one's which. So Leo the lion went grr. Loss of electrons is oxidation. Gain of electrons is reduction, or oil rig was the one I was actually taught to learn. Oxidation is loss. Reduction is gain. So if either of those mnemonics help you, great, more power to you. You could just remember oxidation produces electrons, reduction requires electrons, whatever works for you. The chemical being oxidized can also be called the reducing agent. I wanted to make you aware of these definitions. It's called the reducing agent since it supplies the electrons that are reducing the other chemical. So if something is being oxidized, you can also call it the reducing agent because it's giving electrons that can be reused to reduce the other chemical. Similarly, the chemical that's being reduced can be called the oxidizing agent because it's basically taking those electrons from the other chemical. In a redox reaction, the number of atoms on both sides of the reaction must balance, just like every other type of reaction. If there's 5 hydrogen atoms on the left, you need 5 on the right. But the thing that matters in redox reactions is not only do you have to balance everything else, but you also have to balance the charge. So the charges on both sides must balance. Why? Because if your oxidation is producing 5 electrons, those 5 electrons need to go somewhere. And so you have to make sure your reduction reaction requires 5 electrons. And so that's what it means to balance out the charges, is as you produce them with oxidation, you better be accepting them with reduction. So let's look at a couple of examples that kind of will illustrate that. If you're asked the question, which of the below species is reduced, what would we say? Alternatively, how would we balance this equation? So kind of looking at the first question, it may be easy just to kind of look at it, but that question gets harder with time. And we'll think about that a little bit. The second question, how do you balance the equation? That's where it really matters. You might look at it and say, oh, well, there's Sn on the left, there's Sn on the right, there's silver on the left, there's silver on the right. We got both of them. We're balanced, we're good. But I were to tell you that this is not balanced, I would be right. If you were to tell me this is not balanced, you would be right. Why not? Because the charges are not balanced. So before we get into the question of which of the below species is reduced, let's talk about balancing this equation. So I kind of have 4 steps that I use in balancing equations. Number 1, write half reactions. We'll show you how to do that. Number 2, add electrons to the correct size of each half reaction. Then determine which species is oxidized and reduced. So that's where you get to answer the first question. Then the last step is balance the number of electrons by multiplying half reactions by whole numbers. So let's go ahead and do this. Let's follow the step-by-step guide and let's go ahead and figure out which of the below species is reduced and how we would balance this equation. Alright, so the first step is write half reactions. So what I mean by that is let's write each species by itself and break it down into half reactions. So on the left we've got tin producing tin and we have silver producing silver. Alright, so which of these needs to have electrons added to the left side of the reaction and which one needs electrons added to the right side? Okay, so charges need to balance. What's the charge of one electron? -1. So start with our first line. With 10, we have a charge of 2+. What's the charge on the right-hand side of the equation? Does it have a charge? It doesn't. So if it doesn't have a charge listed, what do we know for sure its charge is? We know its charge is 0. So how many negative charges do we need in order to go from 10 2+ to 10 0? We need 2 negative charges. We can't just write electrons with -2 because every electron just has -1 charge. So instead we say plus 2 electrons, because now we have 2 positive charges on the left plus 2 negative charges. Those balance out to give us a charge of 0 on the right. That's our first half reaction. Now our second one, silver yields silver plus. Do we want to add electrons on the left or do we want to add electrons to the right? You're just adding electrons to whichever charge makes sense. If we add electrons on the left, then we've got 0 plus a negative would be -1 on the left, and on the right we'd still have a +1, so it's not balanced. Instead we have to add them on the right hand side. If we add 1 electron, +1 plus a -1 gives us a charge of 0, which is the charge that the left hand side produces. Okay, at this point now we have written both half reactions and we have added electrons to the correct side of each half reaction, because now each half reaction is balanced. We haven't balanced the whole equation yet, we've balanced each half reaction because the charge is balanced for both of them and we have the correct number of atoms on both sides. At this point then we can determine which species is oxidized and which one is reduced. So for 10, did we gain electrons or did we lose electrons? So with 10, electrons were gained. You can also note that electrons are our reactants. Or they're on the left-hand side of the arrow. Anytime you see that, electrons being gains, electrons are reactants, electrons are on the left-hand side of the arrow, what does that mean? If you're gaining electrons, is that reduction or oxidation? Reduction. Okay. If you're losing electrons, your electrons are a product, and they're on the right-hand side. That is oxidation. Okay. We'll go ahead and box this off just so it doesn't confuse us. So now we have figured out which one is oxidized and which one's reduced. So which of the below species is reduced? Sn. And now our last step is to balance it. Now, it's not balanced right away. Why not? Because there are 2 electrons on the left-hand side of our arrows, and there's 1 electron on our right-hand side, so they're not balanced. Kind of what we're doing is we're adding the 2 reactions together, because when you add half reactions together, you get a full whole reaction. So when we're adding them together, at this point we have 2 electrons on the left, 1 electron on the right. So what can we do to make it so we have the same number of electrons on the left as we do on the right? Our fourth step, if you remember from the previous slide, was to balance our number of electrons by multiplying half reactions by whole numbers. So if we take this whole half reaction, I know it's kind of a funny way of saying it, whole half reaction, but if we take that whole half reaction and multiply it by 2, then that's the same thing as saying 2Ag yields 2Ag plus 2 electrons. We multiplied every single coefficient by 2. Then we still have the same, we didn't change our second equation. Now we have 2 electrons on the left and 2 electrons on the right. So that means we can now cancel our electrons and add our 2 half reactions to get 2 silvers plus 1 tin 2 plus yields 2 silver pluses plus 10. And notice this now is our final complete balanced reaction. So even though it looked balanced at the beginning, it wasn't because electrons were not balanced. So that's how you balance an equation. Let's look at another example. We want to check and figure out which species is reduced and how would we balance that equation. So we want to balance it and figure out which one is reduced. So to begin with, we want to write down both of our half reactions. So we have iron 3 plus, and I always just leave a space for the electrons. That lets me decide whether or not I'm putting them in at a later moment. So I'm writing each of the elements down. Okay, this one's a little tricky one right off the bat. Why do I say that? Well, because if we look at just the atoms themselves, they're not balanced yet, even before we add electrons into the mix. What would we need to do in order to balance out our iodines? Are they balanced right now? Our irons are. There's one iron atom on the left and one iron atom on the right, but our iodines are not. So we'd originally have to start out with the 2 right there for iodine. That's what makes that a little bit tricky, is when you're writing out its half reactions, you have to remember atoms matter. You can't forget about them. So iron 3 plus going to iron 2 plus. Which side do we need to write our electrons on? The left. Why the left? Because electrons have a negative charge. 3 minus 1 yields 2. So now the top half reaction is balanced because we have a charge of 2 plus on both sides. So if we wrote electrons on the left for the top reaction, we should write them on the right for the bottom. So how many negative charges are on the left-hand side now? Is it 1 or is it 2? I hope you said 2, because there are 2 I minuses. So if there are 2 I minuses, you got 2 negative charges. So that means we need 2 electrons on the right-hand side. So now we have negative 2 charge for our iodines on the right and negative 2 charge for iodines on the left. So now, which one is oxidized? Which one has been reduced? Which one gained electrons? Our iron, so it was reduced. Which one was oxidized? Our iodine. So now we have to balance them. What can we do to balance? We have 2 electrons transpositioning in the second reaction, so we need to multiply the top by 2. And sometimes you'll have to multiply both equations by a common number in order to get to the lowest common multiple, and that's okay. Alright, so let's rewrite our iron then. Fe3 plus 2 electrons yields 2 iron 2 pluses. Now we can add them all together. Our 2 electrons cancel, and we're left with 2 I minus plus 2 iron 3 plus yields I2 plus 2 Fe2 plus. And that is our final balanced reaction. And we've already identified which one is reduced and which one is oxidized. So this is a step-by-step way you take and balance a reaction. Sometimes it's not this easy though. Sometimes whenever you don't have just individual atoms, sometimes you have molecules. Some of the most common fuel cells, electrochemical experiments, they're not done with just 2 different metals. The easiest one is the picture we showed you on the first slide that showed the iron and the zinc, and you're producing a charge at the light bulb. That's like some of your batteries, but some batteries are more complicated. And so because of that, we have to use what's called oxidation states to help assign charge to specific atoms. And assigning those charges to those specific atoms will then make it just as easy as what we just did to figure out which one's reduced and which one's oxidized inside of a chemical reaction. Rules for assigning oxidation states. Our first rule is if it's a neutral element, the oxidation state is 0. So these are our elemental compounds. They can be molecules, they can be atoms. So for instance, zinc doesn't have a charge on it, so its oxidation state is 0. Sodium doesn't have a charge listed next to it, 0. Oxygen, because it's only oxygen inside of that molecule, oxygen, the individual oxygen atoms within O2, both have oxidation states of 0. It makes sense because let's say you've got your O2, right? Is that a polar molecule? No. So you do not expect there to be an uneven distribution of charges. So if, say, one of them had a negative one, the other one could have a positive one, and it would still be a neutral molecule. But why would they do that? It makes more sense for them to share electrons. And because of that, they're all going to equally share them, so that means everything's got to be 0 if the whole molecule is 0. Same thing for sulfur. S8, every individual sulfur atom within S8 better have a charge, an oxidation state of 0. The second rule, monoatomic ions. The oxidation number of a monoatomic ion is the same as its charge. So potassium has a +1 next to it, so therefore its oxidation state is +1. Calcium has a 2+ charge, so therefore its oxidation state is +2. Chlorine, -1 charge, oxidation state of -1. Sulfur, -2, so therefore it has an oxidation state of -2. So our first rule is if it's a neutral or elemental form, or if it's molecular, its oxidation state is 0. If it's a monoatomic ion, its oxidation state is the same as its charge. The third rule, assign the charge on a non-metal, which is your anion, to be what it would be from the periodic table, and then assign the metal whatever charge you need it to be for the compound to be neutral. This helps account for those tricky cations that are transition metals that would be like, they could have multiple charge states. So it helps account for your type 2 cations. So let's do some examples. So in potassium oxide, our oxygen. What is oxygen's charge normally in the periodic table? -2. So if oxygen's is -2, what does potassium's have to be in order for this whole molecule to be neutral? +1. Okay, can you kind of see that? K plus, oxygen -2. So remember how we cross the charges? Oops, K2O1. Okay, and so this is exactly how you're going to do it. Assigning oxidation states within ionic compounds is just as easy as it is to figure out what the charge is just looking at the ionic compound. So iron 3 oxide, excuse me. Our oxygen we assign first because it's our anion. It's going to be -2, and our iron is going to be +3. What about this one? You want to give this one a try? Assign oxygen first, -2, so therefore iron has to be +2. So if I were to ask you what is the oxidation state of potassium in the first molecule, it would be +1. What's the oxidation of iron in the last molecule? +2. Our next rule, if you have a covalent compound, and this is truly what oxidation states are made for, is assigning and charge within a covalent compound. The rules for covalent compounds are very particular. You first assign fluorine to be -1. If you don't have fluorine in it, no big deal. Go to the next part of the rule. Then assign hydrogen to be +1. Then assign oxygen to be -2. There are a couple exceptions where hydrogen gets to be -1, but those are typically like nickel, those are like metal hydrides. We're not going to worry about those. Okay, so hydrogen's +1 always, oxygen -2 always. Then assign the other states based on what they would need to be to balance out the charge on the molecule. And don't forget everything you know about ionic compounds too, because those still apply. So the whole crossing of charges still applies. So just work through each one and figure out how to balance out the charge on the whole molecule. So sodium hydroxide. What is oxygen? Oh wait, we assign hydrogen first. So what's hydrogen have to be? +1. What does oxygen have to be? -2. So in order to balance out the charge on our whole molecule, What would sodium have to be? +1. Whenever I said don't forget everything you know about life in general, what I mean by that is you know hydroxide has to have a -1 charge, and therefore sodium has to be +1. That rule still applies. So that's how sodium ended up +1, hydroxide -1. So that means whenever you add oxygen's oxidation state and hydrogen's oxidation state, it should equal -1. Is that true? -2 plus 1 gives me -1. Check. Also, the sum on everything should be 0. So +1 minus 2, and you have to take the number of atoms into consideration as well. So oxygen +1, -2 plus 1. So it's going to be 0. Alright, let's do the next one. So hydrogen, we assign that first. It has to be +1. Oxygen, assign that next. It's got to be -2. So then what is poor carbon? What's its oxidation state? Okay, let's do a little math. What I'm going to do here is charge times the number of atoms. So the charge of hydrogen is +1 times how many hydrogen atoms do I have? 2. And I'm going to add the next atom that I know, oxygen. Oxygen has a charge of -2, and how many atoms does it have? 4. Plus, what's my charge on carbon? I don't know. So that's my X. Then how many carbon atoms do I have? I have 2. Excuse me. What's the charge on the whole molecule? Is there a charge on the whole molecule? I don't see anything written up to the right of the molecule, so no, the charge is 0. So doing this math works every single time. I know lots of students where this confuses them and they just do common sense and figure it out. That's perfect. Don't worry about it. Figure out how you can do it and just work these compounds over and over again as practice, and I think you will get it just fine. So let's finish this math then. So here we have 2 minus -2 times 4, so -8, plus 2x equals 0. So -6 plus 2x equals 0. 2x equals 6. X equals 3. So what's our charge on carbon? +3. Okay. And notice we could add them all up and make sure it all works. There's 2 hydrogens. There are 4 oxygens. There are 2 carbons, just to recheck ourselves. So +2 minus 8 plus 6 gives us 0. Let's do the last one. Alright, so this one's helpful where I say, don't forget everything you ever learned. So we've got oxygen minus 2, hydrogen, +1. So then chromium, what's chromium's charge? +3. How did I know that so fast? I could have done all the math like I did before, but I know that whenever chromium hydroxide dissociates, it's going to form -1. It's going to form chromium 3+ and hydroxide -1. Do that balances out? It definitely does balance out. Okay, because if you take -2 plus 1, that gives you your -1 charge on hydroxide. There are 3 hydroxide molecules, so that gives you a total of -3 on the right and +3 on chromium. So those would be your oxidation states of every individual atom within this molecule. Next rule. Number 5, charge compounds. You want to complete them the exact same way as what we just did for covalent compounds, except now the total of the charges must add up to the total on the compound. So that math that we did previously, it shouldn't add up to 0 anymore. It should add up to the charge that you see present on the compounds. So oxygen, what's oxygen always? -2. What's chromium? We don't know. It's hard to tell immediately. Okay, once again, you can use kind of common sense and play with the numbers, but if you're mathematically inclined, I always set it up the same way. There are 7 oxygen atoms. I'm going to do atoms and then charge on this one. I think I did the opposite. It doesn't matter. Okay, 7 oxygen atoms times the charge of -2 plus 2 chromium atoms times the charge of X equals the charge on the compound, which is -2. So negative 14 plus 2x equals negative 2. 2x equals 2 plus 14, so we got 14 minus 2 would give me 12. X equals 6, so chromium equals positive 6. Okay, next one. Oxygen is negative 2. Manganese is our unknown. So we've got 4 oxygen atoms times negative 2 plus, there's 1 manganese atom, times our charge is unknown, but we end up with negative 1 as the total charge on the molecule. So we have negative 8 plus x equals negative 1, so x equals positive 7. And that's our charge, or our oxidation state on manganese. So let's practice. What I want you to do is just pause the screen right now and determine the oxidation state of each element in all of the below examples. Alright, so ammonia. Hydrogen goes first, and it is plus 1, and then that means that nitrogen has to be negative 3. Oxygen, negative 2, that means zinc has to be plus 2. Water, H2O. Hydrogen, plus 1. Oxygen, negative 2. Carbon dioxide, CO2. Oxygen, negative 2. Carbon, what was it? Plus 4. Nitrogen, did you just write N for nitrogen? I hope you wrote N2. Why N2? Because it's diatomic. All of those 7 atoms, remember, might have been a couple lectures ago, that form the 7 on the periodic table, your nitrogen, your oxygen, your hydrogen is the exception up in the top left. All of those atoms form diatomic molecules at normal temperatures and pressure. So, nitrogen, what would it be? 0. It really doesn't matter because nitrogen by itself would also be 0. But N2, going to be 0. Alright, here's a couple more. Give these all a try. Take a minute, pause the screen, write down what the oxidation state of each of these elements here is, and then come back for the answers. So, iron 3 oxide. Oxygen, negative 2. Iron, plus 3. Sodium sulfate. Alright, so this one's kind of fun. Oxygen's the one that's known right off the bat. Negative 2. This is where you don't forget your common sense. Sodium sulfate, what does that break down into? Na plus and sulfate 2 minus. So that means your sulfur and your oxygen have to add together to give you your 2 minus, and that means your sodium is known right off the bat as plus 1. Alright, so what does that leave your sulfur being? Plus 6. Aluminum hydroxide, once again, don't forget your common sense. Aluminum 3 plus, hydroxide, negative 1. So, aluminum 3 plus, or plus 3, oxygen minus 2, hydrogen plus 1. Hydroxide, this one is easy. Plus 1, oxygen minus 1, whoops, minus 2, excuse me. Dichromate. So this one has oxygen with a negative 2. Did I just do this one? I think I might have just done this one. Oxygen, negative 2. Chromium, positive 6. I think we did a similar one, not this exact one. Okay. Let me know if you have any questions. Feel free to email me about any of these examples that you need further help with. Alright, so now, this is the whole kind of point of the lesson. You can now use what you learned about oxidation states to determine oxidation and oxidize and reduce species in more complicated reactions. So before it was just 2 elements, and you could then decide which one was oxidized and reduced. But now you can do more complex oxidation and reduction problems. So, you want to do the exact same things you did before. You want to figure out first, you want to start out by determining which one changed oxidation state, and that could make it so that you can figure out which one's oxidized and which one's reduced. You could also go further on and do the half reactions if you want to. We're not going to worry about doing the half reactions today. Today we're just going to focus on which one is oxidized, which one is reduced. So for instance, what I suggest doing is write down every element that is in the reaction down the middle. Now, on the left-hand side, we're going to write down which one's all the oxidation states of these atoms as they exist on the left-hand side, and then we're going to write down the oxidation states of each of these elements as they exist on the right-hand side of the reaction. So calcium, what's its charge on the left-hand side? 0. What's hydrogen's charge on the left-hand side? +1. What's oxygen's charge? -2. Oxidation state, excuse me. On the right-hand side, what is calcium's oxidation state in this molecule? Calcium's oxidation state in this molecule then would be 2+, because it needs to balance out the oxygen. Oxygen's oxidation state is still -2. What about hydrogen? What's hydrogen's oxidation state in this example? It's going to be 0, because it's listed as in its molecular form where it's all by itself, and so each individual hydrogen atom inside of H2 is going to be 0. Alright, so what that means is oxygen didn't change its oxidation state, so I will scribble that out, because now we can just focus on the two that changed oxidation state. So, which of these increased their oxidation state, meaning increased in charge? Calcium did. Increased oxidation state. Whereas hydrogen decreased its oxidation state. So if I asked you which of these is going to be reduced, what would you say? Which one was reduced in charge? That's right, the hydrogen was reduced, and that means your calcium was oxidized. So if we were to ask which element was oxidized in this example, you could say calcium. And which element was reduced? Hydrogen. Let's do more examples. Determine which one is oxidized and which one's reduced. So we have hydrogen and we have oxygen. So hydrogen, its oxidation state on the left-hand side, and notice these are already balanced, is 0. What's oxygen's oxidation state on the left-hand side? 0. What's hydrogen's oxidation state on the right-hand side? +1, and oxygen's is -2. So which one of these had a decrease in oxidation state? Oxygen. So that means it's reduced and hydrogen is oxidized. Let's do another example. So now we've got copper and silver. So we've got copper and silver. On the left-hand side, copper has an oxidation state of 0, silver has an oxidation state of +1. On the right-hand side, copper has an oxidation state of 2+, and silver has an oxidation state of 0. How did I know that? Well, if it's elemental, it's 0. If it's an ion, it's the charge of the ion. So which of these elements was reduced? Which one had a reduction in charge? Silver was reduced, and that leaves you with copper being oxidized. One last example. So now we have silver, sulfur, and aluminum. What is silver's oxidation state on the left-hand side? Well, if you know sulfur, because sulfur isn't one of your transition metals, you know sulfur has to be -2. Silver, that leaves silver being a +1. And aluminum on the left-hand side has to be 0. Now on the right-hand side, silver is 0. Sulfur once again is -2 because it's an ion, and it's in an ionic compound. And that leaves aluminum with being +3. So that leaves sulfur being a spectator. So we can scribble it out. And now between silver and aluminum, which one was reduced? Silver. Which one was oxidized? Aluminum, because it increased in charge and silver decreased in charge. So to kind of recap your lesson today, redox reactions must be balanced in both charge and the number and type of atoms. So we kind of added an extra element into balancing. Reduction is gain of electrons, oxidation is loss of electrons. Oxidation state rules help you determine the charge associated with an atom when it exists within a compound, and that's really the whole reason we do oxidation states. Oxidation states will then help you determine the reduced and oxidized species within a reaction.